In this, the final module of Lecture 2, we'll look at how to solve a system of two linear equations. Here we have two equations and two variables, so two unknowns. The linear equations, so we don't have any squared or cubed values. Each equation is a linear relationship between the two variables. There are two methods that we can use to solve these equations. The first is by substitution, the second by elimination. Naturally, they give us equal answers. Before we go on to the best way to see how this is done is through an example. But before we do that, let's see what it means to solve a pair of simultaneous equations. Here we've graphed those two equations. We have equation 1, 8x plus y is equal to 63. And this is equation 2, 9x minus 12y is equal to minus 21. What we mean by solving these equations is to see the point or points where they both hold. Well, if they're linear equations, there'll be only one point, and that's where they intersect. So we want to find the values of x and y where our two lines intersect. Let's see how we do that, first by substitution, then by elimination. Having looked at an example of how we solve equations in practice, let's consider a bit of theory. If we generalize our two equations, so we replace the numbers of the coefficients and the constants by letters, we'll have our two linear equations as ax plus by is equal to c and dx plus ey is equal to f. We can apply those methods we just looked at to solve these equations for x and y, and the general solutions are these. We'll have x is equal to ce minus bf divided by ae on bd, and y is equal to af minus cd divided by ae on bd. Now, we've got a condition there, provided ae is not equal to bd. Well, we know if ae equals bd, that's equal to 0, and our ratio is undefined. But let's look at why that's the case, that we don't have a solution. Here are our two equations. Let's rearrange them so we have y on the left-hand side and x on the right-hand side. We can subtract ax from both sides and then divide by b. So we see that a on b is equal to the slope, and c on b is the intercept. Similarly for 2, y is equal to f divided by e minus d divided by e on x. Again, we have the intercept and the slope. We had our condition that ae can't equal bd. Let's look at when they are equal. If ae is equal to bd, we can rearrange that. That implies that a on b, so dividing through by b, is equal to d on e. So going back, we have a on b and d on e there. If a on b is equal to d on e, then the slopes are equal. If the slopes are equal, then our lines can't intersect, but we have two possible cases. What we want to consider is the numerator for our solution to x, ce minus bf. First, let's look at the case where ae equals bd, so the slopes are equal, but bf is not equal to ce. bf is not equal to ce. Again, we can rearrange that. So we'll have f divided by e is not equal to c divided by b. Again, going back to our rearranged equations, we see that c divided by b is the intercept of equation 1, and f divided by e is the intercept of equation 2. So if f divided by e is not equal to c divided by b, then the intercepts of our two lines are not equal. We can see an example of this. So here we have two lines. They're parallel, so they have an equal slope, but their intercepts are different. There's no solution because they don't intersect. The other case is where BF is equal to CE. So rearranging, we'll have F on E is equal to C on B. That is equal intercepts. What happens then? We have the slopes are equal and the intercepts are equal. Well, in that case, we really only have one line. So here we have equation 2 superimposed on equation 1. In effect, we have one line. So there are an infinite many solutions. So we see to have a solution for our system of two linear equations, we need each equation to have a different intercept on the y-axis and a different slope. And then we'll cross over and we'll have a solution. We'll finish the module with another example. Here we have 4x minus 3y is equal to 1 and 2x plus 9y is equal to 4. You can see how this is solved on a separate video.